Grignard reaction proceeds with a complete racemization, while an SN2 reaction proceeds with a complete inversion. Why? In order to understand these concepts, we need to learn some elementary concepts of stereochemical principles and notations, such as plane polarized light, asymmetry, chirality, racemization, inversion of configuration, and retention of configuration. Let's start our discussion with plane polarized light and optical activity. Ordinary light is light vibrating in all directions through the line of propagation. When ordinary light is passed through a lens made of Polaroid, or more traditionally calcite, it produces a light that vibrates in only one plane and is called plane polarized light. When plane polarized light is passed through a solution of certain compounds, they rotate the plane polarized light in a specific direction. Such compounds are called optically active compounds. Let us see how this rotation of the plane of polarized light or optical activity can be detected. The angle by which plane polarized light is rotated is measured by an instrument called a polarimeter. It consists of a light source, two lenses, and a tube between the lenses to hold the substance that is being examined for optical activity. This arrangement is schematically represented as shown here. If a substance rotates plane polarized light to the right or clockwise, as seen by an observer towards whom the light is approaching, then it is called dextrorotatory or D-form. It is indicated by placing a plus sign before the degree of rotation. In Greek, dextro means right rotating, and hence the term dextrorotatory. On the other hand, if a substance rotates plane polarized light to the left angle or counterclockwise direction, as seen by an observer towards whom the light is approaching, then the compound is said to be Laevorotatory or L-form. It is indicated by placing a minus sign before the degree of rotation. In Greek, levo means left rotating, and hence the term Laevorotatory. For example, the lactic acid extracted from muscle tissue rotates plane polarized light to the right, and hence is known as dextrorotatory lactic acid or plus lactic acid. Similarly, the 2-methyl-1-butanol obtained from fusel oil rotates plane polarized light to the left, and it is known as Laevorotatory 2-methyl-1-butanol or minus 2-methyl-1-butanol. Such plus or minus isomers of a compound are called optical isomers, and the phenomenon is known as optical isomerism. According to Louis Pasteur, a noted scientist, the optical activity of a compound is associated with the three-dimensional arrangement of atoms in a molecule. The two forms of crystals of certain compounds in their aqueous solutions show optical rotation, equal in magnitude but opposite in direction. He concluded that the difference in optical activity is due to the difference in the three-dimensional arrangement of atoms in the two types of crystals. Later, a Dutch scientist, J. van 't Hoff, and a French scientist, C. Lebel, independently argued that if all the four substituents or groups attached to the central carbon atom are different, then such a carbon is said to be an asymmetric carbon or stereocenter. The resulting molecule is said to be an asymmetric molecule. This asymmetry of the molecule is responsible for optical activity. You see symmetry and asymmetry commonly in your everyday life. For example, a sphere, a cone, and a cube are identical to their mirror images and are superimposable. However, many objects are non-superimposable on their mirror images. For example, the left hand and the right hand are mirror images of each other, but they do not superimpose, and hence are said to be non-superimposable. Objects that are non-superimposable on their mirror images are said to be chiral, and this property is known as chirality. On the other hand, objects that are superimposable on their mirror images are called achiral. Let us apply this concept to organic molecules. Chiral molecules may contain one or more asymmetric carbons or stereocenters. An asymmetric carbon is represented with a star on it. Consider two simple molecules, propan-2-ol and butan-2-ol, and their mirror images as shown here. Propan-2-ol does not contain an asymmetric center, since the four groups attached to the tetrahedral carbon are not all different. Thus, it is an achiral. However, butan-2-ol contains four different groups attached to the tetrahedral carbon. Hence, it is an asymmetric molecule and is expected to be chiral and optically active. Some common examples of chiral molecules are 2-chlorobutane, 2,3-dihydroxypropanol, lactic acid, and mandelic acid. Non-superimposable mirror image isomers are known as enantiomers. Enantiomers possess identical physical properties like melting points, boiling points, solubility, and refractive index. They only differ with respect to the direction of rotation of plane polarized light. They can either be dextrorotatory or Laevorotatory. If a mixture contains equimolar proportions of enantiomers, then it shows zero optical rotation. Such a mixture is known as racemic modification. A racemic mixture is represented with the symbol Dl or plus minus before the name of the compound. The process of the formation of an equimolar proportion of an enantiomeric mixture from an optically pure compound is known as racemisation. Another important concept is that of retention and inversion of configuration. Retention of configuration is the preservation of the integrity of the spatial arrangement of bonds to an asymmetric center during a chemical transformation. For example, in the conversion of a chemical species XCABC to YCABC, the relative configuration of the reactant XCABC is retained in the product. In general, if there is no detachment of the bond attached to the stereocenter in the chemical transformation, then the product will have the same configuration of the groups around the stereocenter as that of the reactant or the substrate. Such a reaction is said to proceed with retention of configuration. In the reaction that takes place when -2-methylbutane 1-ol is heated with concentrated hydrochloric acid, there is retention of configuration as shown here. Inversion of configuration in a reaction yields a product whose configuration is opposite to that of the reactant or the substrate. For example, when -2-bromooctane reacts with sodium hydroxide in a reaction that follows second-order kinetics, +2-octanol with inverted configuration is obtained. You are already familiar with the reaction mechanism of nucleophilic substitution reactions of alkyl halides. An SN1 reaction is accompanied by racemisation, while an SN2 reaction proceeds with inversion of configuration. Can you think why? We can illustrate the stereochemical aspects by taking the example of an optically active alkyl halide as a substrate. In this process, if the reaction conditions are favorable for first-order kinetics, then it follows the mechanism of an SN1 reaction. This mechanism proceeds in two steps. In the first step, which is the slow step, the alkyl halide undergoes ionization and forms a stable carbocation intermediate. This intermediate is sp2 hybridized and has a planar geometry as shown here. In the second step, the attack of the nucleophile on the planar carbocation intermediate can take place from either face with equal ease. This results in the formation of a mixture of products in equal quantities, and this process is known as racemisation. In one of these products, there is inversion of configuration, while in the other, the configuration is retained. Thus, the SN1 mechanism is accompanied by racemisation. It is clear that the formation of the inversion product is due to the attack of the nucleophile on the planar carbocation intermediate from the side opposite to that of the leaving group. On the other hand, the formation of the retention product is due to the attack of the nucleophile on the planar carbocation from the side same as that of the leaving group. An example of this type of reaction is the hydrolysis of optically active -2-bromobutane yields a mixture of plus and -2-butanol. Remember that it's a racemisation process. Now, if the reaction conditions are extremely favorable for second-order kinetics, then the alkyl halides follow the SN2 reaction mechanism. It's a concerted process. That is, it proceeds in a single step. Here, the nucleophile attacks from the direction opposite to that of the leaving group, which is also known as a backside attack. In this process, the displacement of the leaving group from the carbon atom of the substrate and the formation of a new bond with the nucleophile take place simultaneously. This results in an unstable transition state with 5 bonds. These bonds in transition state are distorted from the tetrahedral geometry of an alkyl halide. They exist as a planar spoke arrangement for a short time. Then, the leaving group is expelled and results in a product with a complete inversion of configuration. This is known as umbrella inversion. Thus, the SN2 mechanism is accompanied by a complete inversion of configuration. An example is the reaction of -2-bromooctane with sodium hydroxide to form +octane 2-ol with a complete inversion of configuration. You will learn about elimination reactions of haloalkanes and also their reactions with metals. Apart from undergoing substitution reactions, haloalkanes also undergo elimination reactions. In these reactions, a haloalkane with a beta hydrogen atom, on heating with an alcoholic solution of potassium hydroxide, loses a halogen atom from the alpha carbon and a hydrogen atom from the beta carbon to form an alkene molecule. Since a beta hydrogen atom is involved in the elimination, these reactions are often called beta elimination reactions. What if there is more than one beta hydrogen in the molecule? In this situation, more than one possible product can be formed. In such cases, the major product can be predicted by Zaitsev's rule or Zaitsev's rule. According to this rule, in dehydrohalogenation reactions, the preferred product is the alkene that has the greater number of alkyl groups attached to the doubly bonded carbon atoms. Let's look at an example. Looking at the reactant molecule, we see that there are 2 beta carbons, one on either side of the carbon attached to the chlorine atom. We could remove a hydrogen atom from either beta carbon, leading to 2 possible products. When we draw the structure of the 2 products, we see that the first product, formed when a hydrogen atom is removed from the left beta carbon, has 3 alkyl groups linked to the carbons of the double bond. The second product, formed when a hydrogen atom is removed from the right beta carbon, has only 2 alkyl groups attached to the carbons of the double bond. Thus, according to Zaitsev's rule, the first product is the preferred product. Now try a problem on your own. Predict the alkenes that would be formed by the reaction of 2-chloro-2-methylbutane with sodium ethoxide in ethanol. Sodium ethoxide in ethanol is a strong base. Try to work out the answer independently before checking the solution. How can dehydrohalogenation by beta elimination occur in this molecule? The chlorine atom can be removed from carbon number 2. But from the structure, we see that there is a choice of 2 positions from which a hydrogen could be lost. two products will form. Zaitsev's rule predicts which alkene is formed in the greatest amount. 2-methyl-2-butene has 3 alkyl substituents of the double bond. In comparison, 2-methyl-1-butene is disubstituted. Therefore, Zaitsev's rule predicts that 2-methyl-2-butene is the major product. An alkyl halide may either undergo substitution or elimination reaction depending on its nature and on the strength and size of the nucleophile. In the presence of a bulkier nucleophile, elimination is preferred over substitution. Due to the steric factors, the abstraction of proton is comparatively easy than approaching the tetravalent carbon for substitution. For example, primary alkyl halides have little steric hindrance and hence readily undergo SN2 reactions, while tertiary alkyl halides undergo SN1 reactions due to the formation of a stable carbocation. Secondary alkyl halides, depending on the strength of the base or nucleophile, may undergo either substitution or elimination reactions. Now let us look at the reactions of haloalkanes with metals. Most organic chlorides, bromides, and iodides will react with certain metals to form compounds containing carbon-metal bonds. Such compounds are called organometallic compounds. We will discuss two classes of reactions of alkyl halides with metals. One important class of organometallic compounds is called Grignard reagents. Grignard reagents are alkyl magnesium halides. They have the general formula RMgX, where R is an alkyl or aryl group and X is a chloride, bromide, or iodide. A Grignard reagent can be synthesized by combining a haloalkane with magnesium metal in dry ether. A general equation is shown here. Grignard reagents are used in a variety of organic syntheses. For example, bromomethane reacts with magnesium in dry ether to form a Grignard reagent. Methyl magnesium bromide. In a Grignard reagent, the carbon-magnesium bond is covalent but very polar, with the carbon being more electronegative than magnesium. The magnesium-halogen bond is essentially ionic in nature. Grignard reagents are highly reactive compounds. They react with any source of proton, even with weak proton donors such as water, alcohol, or amines, to give hydrocarbons. The reactions of Grignard reagents with water, alcohol, and amines to form alkanes are shown here. This is one of the methods to convert alkyl halides into hydrocarbons. Since Grignard reagents readily react with water, it is very important to prevent them from coming in contact with even traces of moisture. Here's a problem for you to try. What happens when bromocyclohexane is treated with magnesium in dry ether? What will form if this product is then reacted with water? You should recognize that a Grignard reagent will be formed under these conditions. The Grignard reagent is shown in the first equation. Then, if water is present, the Grignard reagent will react to form cyclohexane. One of the oldest organic synthesis reactions is called the Wurtz reaction. Alkyl halides react with sodium in dry ether to make a new carbon-carbon bond, as shown in the general equation. The Wurtz reaction works best to make symmetric alkanes. Polyhalogen compounds are carbon compounds containing more than one halogen atom. Some examples of polyhalogen compounds are shown here. Many polyhalogen compounds are useful in the industry and in agriculture. Dichloromethane, also called methylene chloride, is a colorless volatile liquid with a moderately sweet aroma. Dichloromethane is used as a propellant in aerosols and also as a paint remover. However, the use of dichloromethane for removing paint has been banned by the European Union since it is a carcinogen or a cancer-causing agent. Dichloromethane is also used as a process solvent in the manufacture of drugs. It has additional uses as a metal cleaning and finishing solvent. There are some very real human health risks associated with exposure to dichloromethane. It harms the central nervous system. Exposure to even low levels in the air can lead to slightly impaired hearing and vision. Exposure to higher levels in the air may cause dizziness, nausea, and tingling or numbness in the fingers and toes. The skin may experience an intense burning sensation and mild redness if it comes in direct contact with dichloromethane. If dichloromethane comes in direct contact with the eyes, it may burn the cornea. Trichloromethane, or chloroform, is a colorless, volatile, non-flammable liquid with a sweet odor. It is used as a solvent for fats, alkaloids, iodine, and other substances. It is also used in the synthesis of freon, a refrigerant, or R22 shown here. Many nations are phasing out the use of R22 due to concerns about its role in ozone depletion. Chloroform was once used as a general anesthetic in surgery. However, this use has been discontinued as there are a number of safer alternatives. Exposure to chloroform can cause serious problems to human health. Breathing in chloroform vapors depresses the central nervous system. Not surprising, considering its historical role in anesthesia. Breathing chloroform about 900 parts per million, even for a short time, can cause dizziness, fatigue, and headache. Chronic chloroform exposure may cause damage to the kidneys and liver. In the liver, chloroform is metabolized to form phosgene, a deadly gas. We'll discuss phosgene in greater detail shortly. Some people will develop sores if the skin comes in contact with chloroform. Chloroform is slowly oxidized by air in the presence of light into deadly phosgene gas as shown in the reaction. Therefore, chloroform is stored in dark bottles to prevent exposure to light. The bottles are filled completely to keep air out. For the sake of safety, handle every bottle of chloroform as if it contains phosgene. Wear gloves and eye protection. There are simple tests that you can carry out to determine the presence of phosgene. Phosgene, or carbonyl chloride, has a characteristic odor of cut hay. It is highly toxic. In fact, it was used as a chemical warfare agent during the First World War. If you detect the odor of freshly cut hay when working with chloroform, you should seek medical attention. Chloroform contaminated by phosgene should not be used and should be properly disposed of as chemical waste. Triiodomethane or iodoform is a pale yellow crystalline solid. This volatile compound has a pungent, medicine-like odor. Iodoform has uses as an antiseptic. Gauze packing with iodoform is used in medical applications. However, the antiseptic properties are due to the liberation of free iodine, not the triiodomethane molecule itself. Due to iodoform's penetrating odor, other antiseptics are used more commonly. Carbon tetrachloride or tetrachloromethane is a clear liquid with a sweet smell. Carbon tetrachloride has a variety of uses, including in the manufacture of refrigerants and aerosol propellants. It is used in the synthesis of chlorofluorocarbons. It is widely used as a solvent. Due to safety concerns, many chemists prefer to use other solvents. In the past, carbon tetrachloride was used as a dry cleaning fluid, a degreasing agent and spot remover, and also as a fire extinguisher. These uses have been generally phased out to minimize health risks. The health risks associated with carbon tetrachloride are very serious, as the substance is a suspected carcinogen. Chronic exposure to carbon tetrachloride may cause liver cancer in humans. Kidney damage is also a risk. The side effects of exposure to carbon tetrachloride include dizziness, lightheadedness, nausea, and vomiting. It causes eye irritation and may lead to an irregular or stopped heartbeat. Continued exposure can lead to unconsciousness, coma, or even death. Carbon tetrachloride has been linked to the depletion of the ozone layer. Depletion of the ozone layer increases our exposure to ultraviolet light, leading to a higher risk of skin cancer, eye diseases, and disorders, and possible disruption of the immune system. Freon is the name given to a class of compounds that are chlorofluorocarbon derivatives of methane and ethane. These compounds are extremely stable and unreactive. They are non-toxic, non-corrosive, and easily liquefiable gases. Freon 12, illustrated here, was one of the most commonly used freons in the industry. It is manufactured from carbon tetrachloride by the Wurtz reaction. Former uses of Freon 12 included aerosol propellants, refrigeration, and air conditioning. Since 1994, the use of Freon 12 is being phased out according to the Montreal Protocol due to environmental concerns. Freon 12 and other chlorofluorocarbons are known to initiate radical chain reactions that lead to the destruction of the ozone layer. The final compound that we'll discuss is known as DDT. Paul Mueller was awarded the Nobel Prize in Physiology and Medicine in 1948 for his discovery that DDT could be used as an insecticide. DDT has been used to prevent insect-transmitted human diseases, such as malaria, spread by mosquitoes, and typhus, spread by lice. However, many insect species develop resistance to DDT limiting its effectiveness. DDT is toxic to many species of fish. For certain species of birds, such as ospreys, eagles, pelicans, falcons, and hawks, DDT exposure leads to thinning of eggshells, causing serious population declines. DDT is stored in the fatty tissue of the body and is metabolized very slowly. As a result, it persists in animals and becomes more concentrated in species higher in the food chain. The use of DDT in agriculture has led to measurable DDT levels in humans. The use of DDT was banned in the United States in 1973. However, it is still in use in some parts of the world.